Hi everyone. Here in this video we'll use the concept of buoyant force to solve this problem as preparation for your upcoming exam. And then on a separate video I'll use Bernoulli's equation to again help you prepare for the unit exam. And this first problem is about static fluids, right? So we know that buoyant force is a concept of static fluids, whereas Bernoulli's equation is fluid dynamics, right? Because we have moving fluid. Okay, let's get right to it. It says oil having density of 921 kilograms per meter cube floats on water. A rectangular block of wood 4.23 centimeters high and with a density of 967 kilograms per meter cube floats partly in the oil and partly in the water. The oil completely covers the block. How far below the interface between the two liquids is the bottom of the block? Answer in units of meter. Round to the nearest thousandth. Okay, there's a lot of information. But I drew this sketch. The best I can do is 2 dimensions, so take it or leave it. I'm kidding, but I mean that's the best I can do. And we have oil over here, right? And then we have oil, and then we have water. This is our green block. I should have picked a different color, but I mean it is what it is because I drew this before using the highlighter, but I digress. Okay. And what we want to know is this distance, right? We'll label it right now. We want to know this distance over here. That's what we want to know. How far below here when they meet, okay? And the oil covers the block completely. And we have to use, for this one, we have to use the concept of buoyant force, okay? And let's define buoyant force real quick over here in red. So buoyant force, we abbreviated buoyant force as F sub B as in Bravo, as in buoyant. And that is the net upward force on any object, okay, any object in any fluid. And then we also learn when discussing force of buoyancy, buoyant force, Archimedes' principle, which says that the buoyant force is equal to the weight of the displaced fluid. We'll use both of them, okay? So now that we have defined buoyant force, and if you still don't remember what it is, so with the demo we did for buoyant force is I had the basketball, and then we had the bucket of water, and then I placed the basketball, and I said what's going to happen, and then we commonly say it bounces, but it doesn't really bounce. It just, shoots right up, right? And that's because of the buoyant force. Okay. So as usual, let's write down our given. We'll use blue to solve this one. Given. That's ugly, but that's fine. We have the density of oil. Don't forget that the Greek letter for density is rho. And since we're going to have many densities, so I'm going to label oil. Rho oil, or density of oil, has a density of 921 kilograms per meter cubed. And then we have a rectangular block with a height of 4.23 centimeters. Just for consistency, I'm going to write down the density of the block first, right? And I should highlight the stuff, huh? So we have the density of oil, and then we have the density of the block it's rectangular, so we have to that's very important. Okay. There you go. So the density of the block. So block is a long word, so I'm not going to write the word block. Just lowercase b, right? Because capital B is for buoyant force. and that is 967 kilograms per meter cubed, and we know it's has a height h. This is the height of the block. Now, everything is based mostly on the interaction of the block in the fluid, so just h. Okay. And that one is 4.23 centimeters. So we're using meter cube. If we were to use acceleration due to gravity, that would be 9.8 meters per second squared. So we'll convert this one to meters. We know that centimeter is 1/100th of a meter. So we'll just divide by 100. We'll get 0.0423 meters, and that's it, right? Well, we know the density of water because it's floating also in water. So density of W, which is water, 1,000 kilograms per meter cube. And we're trying to find the distance, about how far, so that is normally a distance. That is normally a distance. How far below? We'll label it distance D. Distance D equals question mark. So now we can say, well, this is distance D. This is what we're trying to find, right? The distance below the interface. Okay. And we will label this one right now. Some of you might already know what this distance is based on distance D and height. But let's work with the buoyant force first, okay? And something very important is for us to remember that buoyant force is a net force, which implies more than one force sometimes, which is the case for us, right? Because if it's floating in water, it's not falling, right? Therefore, there's a force acting against gravity, well, by means of the weight of the block. So I drew this block again, so we can do a free body diagram, your favorite, a force diagram. Smooth it just a little bit. And we know the one force we can count on here on Earth is the weight of the object. And we know the weight of the block. Well, the formula for weight is mass times acceleration due to gravity. So the weight of the block would be the mass of the block times acceleration due to gravity. This is floating, it's not moving, it's in equilibrium. Therefore, we should have a force equal in magnitude but opposite in direction, which is acting against gravity. So there you go, equal magnitude, and that is the net. So this is the force of buoyancy, right? Buoyant force. There you go. And that's it, right? There's no motion on the x direction, on the x-axis, just on the y-axis. So now we can sum the forces, right? We can sum the forces. So we have only forces acting along the y direction. We'll make up to be positive, so that'll be force of buoyancy, buoyant force, minus the weight of the block, which is mass of the block, times acceleration due to gravity. That'll be equal to 0, because there's no acceleration, there's no motion. So we can now move the weight of the block to the right side. So we can know the magnitude of the force of gravity. So the magnitude of the force of buoyancy. There you go. Now, what is the force of buoyancy? Well, it's the force on any object in any fluid. So the fluid is applying the force, right? Now we have two different fluids, so we're going to have two different buoyant forces. One of the water and one of the oil, right? Because this is submerging both fluids, and this is a force acting on the object in any fluid, okay? So we have force of buoyancy on the water, force of buoyancy on the oil. So then we can say the buoyant force is the buoyant force of the water plus the buoyant force of the oil, and that is equal to the weight of the block. Okay, now we have to use Archimedes' principle because we know the buoyant force of the water is equal to the weight of the water which was displaced. And we know the formula for weight, mass times acceleration due to gravity. Okay, so to find the weight of the water which was displaced, we can just get the mass of the water times acceleration due to gravity. That is the weight of the displaced water. Likewise, we can do the same thing for the oil. The weight of the oil which was displaced can be found by the mass of the oil times acceleration due to gravity. That is equal to the mass of the block times acceleration due to gravity. And I think you can now see why I did not include lowercase g or acceleration due to gravity, because we can cancel that one. Okay, so now we have the mass. Well, I'm going to continue over here because we're just simplifying. The mass of the block. No, never mind. Let's go down. Just for consistency. So the mass of the water plus the mass of the oil is equal to the mass of the block. Well, we're not giving mass, right? But we're giving density. And we know that the formula for density is mass divided by volume. So we can do some algebra and we can know that, or we can come up with this formula to find the mass, which is the density of a fluid or an object times its volume. So we can now define the mass of the water by means of its density and its volume. So then the mass of the water will be the density of the water, which we do have, times the volume of water, plus the density of the oil times the volume of the oil. That is equal to the density of the block times the volume of the block. Okay, how can we find the volume of the water, the oil, and the block? The easiest one is the block, right? Because we have a block that has a certain height, and if I were a better artist, I can do a three-dimensional sketch, or I don't know the real name for it, so that I could show how the water and oil, or the water more than anything, is pushing against the base, which is a rectangle because it's a rectangular block, and we can find the volume of the block by getting the the area of the base, which is a rectangle, times the height, right? So to find the volume of the block, we can just do area times height. It is not that simple with the water and the oil. Well, if you want to know the volume of water that was displaced by the block, well, we can just find this volume, right? This is the volume that is displaced by the block, the volume of water that is displaced by the block. So it's the area of the base times this height, or distance d. Well, we can do the same thing for the oil, right? We can find this volume, which is the area of the base, or just area, right? Would be the cross-section area, if you want to call it that way, times the height. What is this height? Well, I know this whole thing is h. I know this is d. If I want to know this, I can just take the difference, right? So this will be h minus d. Okay, this is h minus d. And now I can define the volume by means of the area and the different heights, or height, distance d, and the difference. Okay, so density of water, the volume of water will be the area of the block, right, the surface, not surface area of the base, times, so for the water, its height would be distance d, plus the density of the oil, there you go, times its height, which is h minus d. That is equal to the density of the block times the area times distance h. And we can cancel. Uh-oh, I forgot the area over here. That was my mistake. I'm really sorry about that. Area A. There you go. I was getting ahead of myself. Okay, so now we have density of the water times distance d plus density of the oil times h minus d is equal to density of the block times h. Okay, so now this is looking better. We have to find distance d. We have two of them, so we're going to have to factor somehow. So let's just distribute right over here. Let's distribute. And we're going to have density of the water times distance d plus density of oil times h. I have to do maybe a little dot so we know it's multiplication. Minus density of oil times distance d is equal to density of the block times h. Okay, so I can move this one over here, density of the oil times h, so I can have the h's with the h's. I don't know if that's the plural, but h and h over here. So let's do that. Minus density of oil times h minus density of oil times h. This cancels, so now I have density of water times distance d minus density of oil times distance d is equal to density of the block times distance h minus density of oil times distance h. And now I can not only factor distance d, but also height h. So then it'll be d times density of water minus density of oil is equal to h times density of the block minus density of oil. And I'm one step away of solving for distance d. We divide by this difference. There you go. This cancels. Man, I thought I would have enough space, but you guys know how it goes, right? So now we have distance d is equal to height times density of block minus the density of the oil divided by density of the water minus density of the oil. And now we can just use our numbers, right? Use the Inspire calculator. And you know what, let me substitute this first. That way you guys see it. So we have height h, which, man, it was 0.0423, 0.0423 meters. I should have used parentheses. Times, so I'll parentheses and brackets right now. Density of oil, 921. No, sorry, of the block, which is 967. Oops. So 967 kilogram per meter cube minus 921 kilograms per meter cube, parentheses, and then I will add a horizontal line because there's no way I can do it. I can freehand one of those. Now we have the density of the water, which is 1,000 kilograms per meter cube minus 921 kilogram per meter cube, which is the density of the oil. parentheses, parentheses, bracket, bracket. Man, those are some ugly brackets over here. There's a little better. Okay. Now we can find the answer. At this point, you can stop the video. That's fine, because you already know how to do it. But if you want to stay, I appreciate it. So 967 minus 921 divided by 1000 minus 921. And we should get a small number. There you go. So 0.02463 meters. So distance D is equal to 0.02463 meters. And if you're gonna have perspective in centimeters, it would be 2.46 centimeters. So almost 2.5 centimeters, right? And there you go. About half of it, well, a little more than half of it been submerged. And that is it. See you in the next one.